The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, let's get going. So today, let's say a few more words about PDEs, and then we'll leave that topic for a while. I think I'll actually come back and have a little lecture about that at the right before Thanksgiving, for those of you who are still around. And then we'll start talking about probability, and then that will lead into several lectures about models versus data, which is a very important topic for all of you who either plan to generate data or plan to generate models during your stay here, which probably is everybody. So we'll talk about that for a while. So PDEs. I guess the first comment is homework 7. Have any of you looked at this yet? Not a single one. So homework 7 is the same problem that Kristen showed in class in the demo for COMSOL. So, and I want you to solve it both ways. So solve it with COMSOL, and then solve it writing your own finite volume code. And I want to warn you, this problem has a characteristic length that's way smaller than the dimensions of the problem. And so, in principle, you might need to use an incredibly fine mesh to resolve the gradients in the problem. So just remember, so you haven't looked at it. The problem is we have a drug patch. It has some concentration of the drug. The drug is diffusing slowly out of the patch into the flow, and we have some flow here, like that. And the characteristic length is that this is a velocity boundary layer. So the velocity in the x direction is equal to y times something, dvdy, I guess. This is some number. And so this has units of, what is that? Per second. So like a strain rate. Okay. And the diffusion here is controlled by diffusivity, d, and that has units of, say, centimeters squared per second. And so the d over dvx dy, this thing gives a characteristic length squared, which is sort of the natural length scale of this problem. And the problem is that for the drug molecule, it's a big molecule, it's a very small diffusivity. And so therefore, this is a really tiny ratio. And so the L is very small. And similarly, if you look at it from the point of view in the x direction, the Peckley number is really gigantic. And so both of those will tell you that you have to watch out. There might be very sharp gradients in the problem. And if you just think of it physically, right over here, we think the concentration is 0, somewhere over here. And all of a sudden, right here, the concentration is going to be close to the concentration in the patch. So there's almost a discontinuity in the concentration. So there's a really sharp gradient on the upstream edge. And then something funky is going to happen down here at the end of the patch, too. It won't be quite as abrupt, but it could be pretty strange. All right, so you got it? Okay. And in the problem, we want you to figure out the drug diffusing all the way over to here somewhere, way far over there. And so you may need quite a few mesh points in the y direction as well. All right, and this kind of problem, this is a very simple case, right? There's no reactions. The velocity is just in one direction. I mean, this is not a very hard case, but you'll see it's actually still pretty tricky to get the right solution. So don't just believe what the code tells you. If you just run COMSOL and just don't believe it's showing the truth, and don't believe if you just write down some finite volumes that you'll get in the truth. So mess around with it and try to convince yourself it's really converged and you really have the real physical solution. Because you expect a sharp gradient, say, in the upstream edge, you might want to play with using a finer mesh in the x direction here than you would down here. because down here, presumably the gradients in the x direction are much smaller. So you don't have to use square finite volumes. You could use rectangles. Yes?
I don't understand what you have written there. This Vx equals y, dvx y.
Yeah. So that's because the velocity, the Vx is 0 at the wall, and the velocity increases with y. So Vx increases the further you get from y. This is y equals 0. Always going up that way. As you increase the height, the flow gets faster, and that's typical because you have no slip boundary condition at the wall. Is that okay? Or may I misunderstand the question? Ooh, is that good? Okay.
Y is a constant.
Yeah, in this particular problem, this is just a number that we tell you in the problem. Right, if you had a flow in a cylindrical pipe, it wouldn't be right. It wouldn't be a number. It'd be more complicated. Yeah. All right. So this is. I mean, again, this is like the simplest you got. It's only 2D. It's really simple, but you're going to see here that even here you can have a lot of trouble, and if you just don't think about it, the computer will give you an answer. Whatever you put in some finite difference equations or finite element equations or finite volume equations, F solve, whatever it's going to solve and give you some numbers. It doesn't mean it has any relation to the physical reality. So this is a problem to really pay attention to whether you're really converged. All right. And so what I suggest you do in this problem is go through a sequence where you vary. The real problem wants you to do this all the way out to this is 1 centimeter. But I suggest you instead solve a simpler problem where you put here's a simpler problem. Put your boundary right here, really close. And then solve that problem. You won't need as many mesh points across to get from here to here. And this should be, if this is, suppose you choose this as C equals 0 boundary condition for this wall, then this should be an upper bound, because if you put an absorbing layer here, it should drive the diffusion faster, right? So as you increase how far this distance, let's call it little h, as you increase little h, you should converge to the true solution that you want, sort of from above. Does that make sense? Yeah? Is this okay? All right. And similarly, you can vary the mesh, how big your boxes are, say in delta x and delta y. And again, for each of those, you could think about, how should things converge? And so look and see if it's actually converging the way you think it should be converging. All right. Any more questions about this? Okay, so this homework problem might look like a MATLAB coding problem, and has some MATLAB coding, but that's not really what it is. It's really like it's a conceptual problem about what you're doing. All right. All right. In this problem, I want you to use finite volumes. So let's talk about finite volumes for a minute. So finite volumes is to imagine that we have little control volumes, and each one of them has a little propeller in it, stirs it up, like little CSTRs. And so we do it just like you did back in your intro chemie class of mass and energy balances a million years ago. You know that you have some flow coming in here, and maybe some flow going out there, and maybe you have some flux coming in here, and maybe some coming out there. And you can add up all the flows in and all the flows out, and then the net of all those fluxes has got to be equal to the accumulation. And if we're doing a steady state problem, then there's no time derivative, so the accumulation term should be 0. And you did a lot of these problems a long time ago, right? Okay, so you just do it like that. The only problem is now we have a million of these little boxes all coupled to each other. So you get one equation for each box. And in this problem, when you do this method, what people assume is that you have a uniform concentration sort of across here, or the number you use as the average of the concentration in the cell. And so it's not really exactly realistic. So that's where the approximation is. What you're doing at the boundaries is very realistic, because you're actually computing the fluxes across control volumes. Is exactly the way you should do it. So there's different methods, right? Finite element, finite difference, finite volume. The nice thing about finite volume is you're really treating exactly what's happening across the boundaries of the mesh area, the mesh volume. And we'll find that a lot of chemie problems, this is how people prefer to do it. And because you're treating the fluxes exactly, if you have if you have your mesh volume sitting on the wall or on top of the drug patch, suppose it's sitting right on top of the drug patch here, then if you're sitting, well, let's do a wall. Suppose you're sitting on an impermeable wall, then we just know that the flux here will be 0 if it's a wall, right? So that's easy. No flux here. So we only have to worry about this one, and this one. That one's not doing anything, okay? This case, if you're sitting in the drug patch, there is a flux. Stuff's coming in, and you'll need to figure out how to write that boundary condition. So the boundary condition as written is that C of the drug is equal to some number, C drug, whatever it is in the patch. But that's not so easy to impose here. And so there's two ways to look at it. One way is people compute this flux by considering, suppose I know this is C drug here. I'm trying to really figure out what's sort of the average concentration here. And so one way to compute this is to say it's the diffusivity times C drug minus C at the middle over delta Y over 2. That would be the flux. So that's one way to look at it. Another way people look at it is they draw what they call a ghost volume. And so here's my C that I care about, C middle. Here's C ghost. And here's the line between them. Now I can use the same equation here that I would have used before, except I don't know what C ghost is, because this is not really there's no real cell here. This is below the patch. Here's the patch. Right, but I imagine the patch is not there for a second. And I write down the same equation I would have here. And the flux diffusively would have been d C ghost minus C middle over delta Y. Right, that's what you would have written as the diffusive flux. But I don't know what C ghost is. So now I have to think, well, how am I going to estimate what C ghost is? I can say, well, let's do a linear interpolation from this concentration to that concentration. So let's say that the C boundary is equal to C ghost, the average of these two, plus C mid over 2. That's what we got if you did a linear interpolation between these two guys to figure out what it is here. But here we know what it is. We know what C boundary is. Right? That's the concentration of the drug patch. So then we can solve for what C ghost is. Yeah.
How do you know what C mid is?
C middle is the unknown. That's what we're going to compute. We just want an equation that involves C middle because we have C middle as an unknown. We need an equation that involves C middle, just like we would if we have a finite volume that's in the interior somewhere, we have C of this grid point, Cij. We just want equations that involve Cij. But we need an equation that somehow connects it to the boundary conditions. Yeah?
When would you use that second method, since if you know C boundary, it seems to be easier to just do it first?
Right, and actually, I think if you do it this way, in this case, you get the same formula. You should run it out and see.
So when would you use the C ghost?
This C ghost thing is handy when these conditions. Actually, in the finite volumes, this is it. I don't think you need to do it. Maybe you had a velocity flow here. I don't know, but you won't at a wall. So I don't know. In the finite difference method, you can use these ghost points as well to do the flux boundary conditions, and that's often useful to do the ghost thing for if you have a symmetry imposed flux boundary condition. Yeah.
What's the other? So like you have 50 C drug minus C middle. What's like 10 equal to?
That's the flux. The flux is coming across this wall. And we'll have to add that with the flux coming this way, and the flux coming this way, and the flux coming this way to get. to get our total flux, which is going to net out to 0 at steady state. Is that all right? But the other ones, you'll know how to write them, right? They're just full of velocity flows. The nice thing about the finite volume method is that when you're trying to consider the velocity that matters is actually the velocity here. It's what flux that couples the two finite volumes together. So your velocity is sort of being evaluated halfway in between the two mesh point centers. This turns out to make the whole procedure more numerically stable. You compute the flux by, say, the difference between these two. And you're sort of implicitly evaluating right at the halfway in between. Other methods like finite difference, you're sort of trying to get the velocity or the flux at the same point here. And it doesn't really make that much sense from the point of view of trying to compute how much material is close to here to use the velocity right there. And so if you do, when you write down equations, and particularly equations that involve the pressure, so suppose you try to discretize the Navier-Stokes equations, and you have a pressure gradient that's driving the flow, then you have to figure out where you're going to evaluate the pressures and where you're going to evaluate the velocities. And if you try to evaluate them at the same points, it turns out that you get numerically unstable problems. But if you do it by this finite volume method, then it just works out naturally. It's fine. And there's you need special methods if you're going to try to do it where you have the velocity on the mesh at the same points as the pressure mesh. You'll notice in most of the problems we give you, we just leave pressure out. We try to rewrite the equation so no pressure ever appears. And that's because pressure in general is a problem because you can have acoustic waves physically. And if you do the equations which allow for acoustic waves, you'll get them in the numerical solution as well. But usually we don't care about that. So you have sound waves racing around your solution. And that causes a lot of trouble numerically. So a lot of times people rewrite the equations to try to remove the pressure from the equation. So if you write down the Navier-Stokes equations, you guys, you did this in transport, maybe you'll study that today in the class, in the test, I don't know. Anyway, there's a pressure term, right, if you just write it naturally. But oftentimes you can remove that by an equation of state, for example, and then you can get rid of it, and that turns out to be better for numerical solution. All right. Yes?
Another question. So we've said that for this problem, especially, the length scale is very small. So that means that these finite volume cells are necessarily also going to have to be very small, which means we have to do a lot of them to go over any point. Maxwell gets around this by having kind of a variable volume. Do we have to address that somehow in MATLAB and have some variable volume?
Okay, so from the point of view of writing a code, it's a lot easier to write it with fixed mesh because all the equations look exactly the same. So I suggest you start that way. And if you use a very small value of h, then I think you'll be able to solve it no problem. You'll have enough mesh. Then once you figure out how to do that, now you might be able to see, okay, can my solver solve this? And then that gets into another question. Actually, what solver are you going to use? So any ideas about this problem? So you could use fsolve, but I'm telling you, you're going to have to use a lot of mesh points. That means that fsolve is going to have to solve for a lot of variables, right? Backslash, it might be. So the key thing about this, the nice thing about this problem is it's a linear differential equation. There's no non-linear terms in it. So when you rewrite the equations as finite volumes, it's all going to be linear in the unknowns. And what else is nice about this problem? When you use a local finite volumes as your, it's going to be super sparse, right? So the matrix that comes in is going to be really sparse. So you want to use some method that can handle gigantic sparse matrices. Okay, so you wrote a code like that earlier, so that'd be one possibility. If you know how to use the right flags in MATLAB to help their built-in solvers handle sparsity, then it should be good. If you just ask it to solve it by dense method, by like LU or something, you're going to have a lot of trouble once you put too many mesh points in there. But you can just experiment. Try bigger and bigger matrices, and then at some point, backslash is going to give you a warning or something, right? Unless you tell it that you're sparse. All right. Any more questions about this? How would people solve it do you think professionally? Suppose I was doing a problem like this in 3D instead of 2D. How would people solve it? What solver would they use? Not SL, no. Yeah, so they would use conjugate gradient. So probably, I think it's called this, ICG stab. That's the program that you would use if you have a really, really gigantic sparse matrix. Okay, so that's the conjugate gradient, and Professor Swan talked about the advantage of that is you never have to actually store the whole matrix. You only need to evaluate the matrix elements, and then you can throw them away. So if you have a very sparse matrix, that's pretty cheap to do. So it's a really good code. I think in this 2D problem, you can probably get away with other solvers. You don't have to use this. But this is definitely a possibility. This is a built-in MATLAB program as well. Be warned, though, this is an iterative solver. It's not just going to be one solve, boom. You know, and it might have troubles. So you might want to go with the other ones. But anyway. Let me ask you a question. How about, do you need an initial guess? What do you think? Depends on the solver, right? So if you solve it with backslash, do you need an initial guess? If you solve it with fsolve, do you have to give an initial guess? If you solve it with by CG stab, do you have to give an initial guess? Yes, right? Okay, so then you have to think about where you get your initial guess too. So this is things to think about. All right. What else to tell you about? Okay, one last thing about PDEs, and we'll come back to this later. So far, we haven't done really anything that's very time dependent, but a lot of real-world PDEs have a time dependent in them. And there's a very important concept, a thing called the CFL number. And this is named after a 1928 paper, and I'll write the guys' names down. And what they showed was that if you're trying to solve a PDE system where you're discretizing in both x and time, that you have a condition, well, you have a number that they defined as delta t times the velocity in the x direction divided by delta x. So that's a dimensionless number. That's a CFL number. You see a lot of papers they'll say what CFL number they used. What that means is that the ratio of their time mesh compared to their space mesh. And conceptually, let's think about what's happening here. So suppose we have a flow flowing in the upwards direction, and we have a bunch of little finite volumes. All right, so we've discretized in delta x already. And this is x. All right, and there's some flow here, and I've already decided somehow what length scale I want to use. So I've decided my delta x. And now I'm trying to figure out what delta t I should use. Now, from the point of view of saving CPU time, I want the delta t to be as giant as possible, right? Because I want to be able to zoom along and predict for long periods of time what's going to happen in my system. But if I make delta t really large, let's think about what might happen. Suppose I choose delta t to be 10 times delta x divided by u. Okay, so that means in my one-time step, I have some guess or some current value of the concentrations in all these finite volumes. And then I wait to a time step that's 10 times delta x over ux. So I had some stuff that was here. Where is that going to be 10 times later? 10 time steps later. 10 blocks up, right? So it's going to be like way up here somewhere, right? And so what's going to happen there is that my numerical methods are all computing stuff locally from the spatial derivatives. But it's crazy if between my time steps, this stuff completely left the picture. It's already convected all the way off the screen. And some new stuff, which was way down here before, is now the stuff that's here. Should be there, if it's physical. Numerically, who knows what will happen if you try to do this. But it won't be good. So the condition is that you need this number to be less than 1, or same order of magnitude as 1. And if you try to make this much bigger than 1, then you're doing something crazy, because you're convecting stuff over multiple mesh points. And so that turns out to be a very serious limitation. If you're trying to do simulations for, let's say, a reacting flow for a long period of time, because you might have to use a really tiny delta t. And then people have developed all different fancy methods to try to get around that. But if you just do the obvious things to do, you'll always run into this limitation, that you need to choose the time so small. All right? And also, it's bad because as you make delta x smaller, which improves your accuracy, I'll have to make your delta t smaller too. But of course, making delta x smaller increases your CPU time because you have more finite volumes to compute. And then you'll also have to make delta t smaller, which means you have to do more time steps too. So it's even like a double whammy. So getting more accuracy is going to really cost you badly. And so this is another reason why people used to always refer to color fluid dynamics. You can make a pretty picture, but it might not be physical at all. Because you can make it solve equations. If you, for example, didn't impose this, then who knows what kind of crazy stuff you'll get. You get something. It'll compute something, but it may have like no relation to the real problem. All right. Okay, I think that's all I want to say about PDEs. Are there any questions about PDEs before I start talking about probability? All right, you got it totally down. I'm looking forward to some really awesome solutions. Homework 7. All right. Actually, just one last comment. If you decide you do want to do adaptive meshing and not use, you want to change your mesh size, you can choose meshes like this if you want. And you can even do things like this, where you have a bigger mesh and then maybe you have 2 smaller meshes underneath it in the next row. Right? So you can just have stuff flowing here, stuff flowing here, stuff flowing there. So you can do all kinds of crazy stuff like this. This can really help improve the accuracy of the solution a lot, but it's, I would say, very prone to bugs. So just, if you do this, be really careful and don't do it too often. I would say you might have a few boundaries where you do something funky like that to change the mesh size. But don't go crazy with it. ComCell is smart. It has a really nice way of doing the meshing for you. So that's like its advantage. Somebody very carefully coded how to handle this kind of stuff in the general case. But for you guys who are doing it first time, it might not be so good. All right. Okie dokie, so that's enough on PDEs. Let's talk about probability. So probability is everywhere, except in undergraduate chemistry homework problems. Okay, so when you did problems as an undergraduate, they always had some nice solution. It was 2 pi, it was 3.0, everything was like deterministic, it was definite. The grader could go through, oh, nope, you're off by 0.1, it couldn't possibly be right. Okay, right? That's like not reality. So anytime you actually make a measurement, you always have measurement noise. And if you try to repeat a measurement, you don't get the same result. Okay, so that's like completely different than an undergraduate problem, right? But this is the reality. So the reality is the world is like not so nice as you think. But actually, it's even more fundamental. It's nothing about, I mean, there's one problem about how good an experimentalist people are and how fancy an apparatus you bought that can make things exactly reproducible. But even if you do that perfectly, the equations we use really don't correspond to the real physical reality. So we always use these continuum equations. You guys are probably studying them a lot in 1040 and 1050, especially 1050, I guess. But those equations are really all derived from like averages over ensembles or little finite volumes or something. If you look into the derivation of the equations, and reality is that the world is full of molecules, and so they're all wiggling around. And if you look in a little finite volume, you look right now, you'll see that there's 27 molecules in there. If you look a second later, there might be 28. Then a little bit later, it might be 26. It's always fluctuating around. Okay, but according to our average equations that we use, like in the Navier-Stokes equations, is always 27.3. right? But of course, it's not 0.3 of a molecule. So it's explicitly it's the average is what we're computing. And the reality is fluctuating around the averages. The same thing in thermo. We say that such and such has a certain amount of energy, but you guys done some stat mech already? Yes? Right, so you saw that's not true, right? So really, all that's saying is that's like the probability, the average. If you had many ensembles that were exactly the same, and you average them all, you get some number, and that's your average energy. But for any actual realization, it has some different value of the energy, right? And it's even worse than that. So that's because we have a lot of particles. You can even go down to like the microscopic level. You have one molecule, and you calculate things about that. It turns out you have to use the Schrodinger equation for that. And the Schrodinger equation explicitly only gives you probability densities. So it just tells you the probability the molecule might be somewhere, the electron might be somewhere, the energy might be something. But it's not actually what it really is. It's just saying a probability distribution. And every time you do the experiment on the molecule, you get a different result. Now, this is super annoying, but it's just the way life is. Einstein got so annoyed, he has a famous saying, God does not play dice. He was like just completely annoyed at these equations. But it's the way it is. So the reality is that all we know about are really our probability distributions. And most of our work and our lives, we always talk about like the mean or the median. And that's what we're talking about as if it's the real number. But really, it's always some distribution. Okay? So it's time, now you guys are in graduate school, it's time to like face up to this. And that's what we're going to talk about for the next week or two. This also makes you wonder what you're doing when you make a measurement. So if you make a measurement, first of all, the fact that when you measure something repeatedly, you're not going to get the same number. That's kind of alarming, because I want to say, I'm 5'9". I should be pretty confident I'm always 5'9". I'm not, but actually, if you measure me multiple times, some guys will get 5'9.25", some people will get 5'8.75". So it might make you worry. Did I change? Maybe I grew between the measurements, right? So that's one issue. Because our experiments are not repeatable, and we get different numbers every time we make a measurement, then we have a big problem. Somebody says, well, I really want to know how tall Professor Green is. I've always wondered, how tall is he? And everybody's telling me a different number, and when you go measure it again, you get a different number again. What's going on? And so you'll have to then we have like a concept that there is a true height of Professor Green. And we just don't know what it is. And then we'll try to maybe make repeated measurements of my height, and then maybe take the average. That would be the obvious thing to do. And we take the average and we'll report that. We'll tell the boss. We'll lie to him. Say, Professor Green's 5'9". When really we never actually measured 5'9". Every time we measured it was 5'9 1/8, 5'8 3/4. Every time it was something different, but we just say, okay, he's 5'9". And the boss, he doesn't want to know about all this complexity anyway, so he just believes you. So he takes your average number. Right, but you know that you're not really sure I'm exactly 5'9", right? And so you have a probability distribution, and you're doing your best guess. And in fact, if you're honest to your boss, you'll give an error bar. You'll say he's 5'9", plus or minus half an inch or something, right? And that way, what you're saying is you're pretty sure the true height of Professor Green is somewhere in that range. All right? Okay, is this okay? Yeah. Now, it might be that I'm actually changing height, right? I get a nice rest. I lie down for a long time. Maybe I stretch out a little bit. When I stand up in front of a lecture here for a long time, I'm shrinking. My vertebrae being compressed by standing here so long. So, it's like a combination of things. One is your measurement instrument is not perfect, and one is that I actually might be fluctuating. Okay? Had a big breakfast. I'm growing. All right. So it's true with everything. Every experiment you do is like this, that there is a real fluctuation of the real physical apparatus, the thing you're trying to measure, because mostly things we're trying to measure have fluctuations intrinsically. And then on top of that, your measurement device is fluctuating, which means, and then the combination is what you're measuring gives you a fluctuation. If you have a very nice instrument, the fluctuation of your instrument is smaller than the fluctuation of the real system. And you'll go down to the limit. Anybody with a really good instrument should measure approximately the same probability distribution, which is the real fluctuation of my height, for example. So if you bought a laser interferometer and mounted a mirror on my head and measured my height to the wavelength of light, you're pretty sure that It's pretty good. It's within a wavelength of light. So the error bar there is just to the fact that I slouch sometimes. Right. So, is that okay? All right. So let's talk about some basic things about probability. So we're always saying there's a probability of an event. And so we want to give a number. So for example, I'm flipping coins. I flip a penny. It could be heads or tails. I'll say the probability of heads is approximately equal to 1/2. Okay? So I flipped a coin, and if you flip the coin 100 times, you might expect to see 50 heads. Now it could be 49 heads. It could be 51 heads. So you have to worry about like exactly how precisely you know it, but you think it's something like 1/2. Now, it just should warn you that I actually didn't specify any more significant figures here, and it might be really hard to figure out what those significant figures are. And this is related to the measurement problem, right? So, we think that a coin is about a 50-50 chance of being heads or tails, but if you really want to prove it, that might be really hard to do. You can have joint probabilities. So suppose I have a penny and I have a dime, and I try to think if I flip them both, what can happen? I could have that they both come up heads. I could have this guy come up heads, this guy tails, this guy tails, this heads, both tails. So there's like 4 possible outcomes, and we think they all have about approximately equal probabilities. Right? So probably any of these things happening should be about 1/4. So you can write the probability of event 1 and event 2. So this would be, for example, the probability that I got heads for penny and heads for dime. And I think that this is about 1/4, right? All right. Now, I could also say the probability of heads and heads is equal to the probability of heads for the penny times a probability of heads for the dime if I got heads for the penny. Now, if these 2 coin flips are completely uncorrelated, then the probability of the heads of the dime with heads of the penny is the same as just the probability of the heads of the dime. So they don't matter. But many things that we'll study are correlated. That the probability of something happens depends on whether something else happened. All right? So this kind of expression is very important. And this is just an equality, and it's sort of like a definition of what these are, right? And I'll just notice that you could write the other way around. So this is the probability of heads of the dime times the probability of heads of the penny. All right. This is okay? So these 2 guys are equal to each other, and you can rearrange that equation any way you want. And we'll come back to a very famous way to rearrange that equation. It's called Bayes' theorem. And that turns out to be really important in model versus static comparisons. Okay. Instead of doing and, you could do or. So maybe you could say, well, what's the probability that I see at least one head? Okay, so I flip my 2 coins, and I have the probability of I see at least one head. Now, so we know that you know intuitively the answer is 3/4, right? Yeah. But let's try to think of where does that really come from. So, what is that? Okay, sorry, it really threw me there. All right, so probably at least one head. It's not equal to the probability of head for the penny plus the probability of head for the dime. Right? Because we know that this is really 3/4, and this is a half, and this is a half. You add them up, half plus a half is not equal to 3/4. So be careful. There's a lot of things you can say quickly that are not true. Right? So anyway, you really have to consider the whole thing. And in the best case, if you can enumerate what's going to happen, then it's pretty simple to add up things. Otherwise, you have to be very careful with the algebra to make sure you add up all things correctly. Okay. So let's see what this should be equal to. So this should be equal to the probability that I had a head on a penny times the probability that I have head for the dime if I had a head for the penny plus probability of the tail for the dime head for the penny plus probability I got a head for the dime and then times something like this too. All right. And in a case like this where I'm summing over all of the possibilities, so in this case, I'm either going to get head for the dime or a tail for the dime. It's not going to balance on its end. I'm assuming that chance is 0. Then these two things just add up to 1. Is that right? Because it's really saying the probability of the dime will do something if I had for head for the penny. Okay, is this all right? So you might want to practice doing little algebra things like this to make sure you know how to do it. All right. Okay. Yes? No? Maybe? Okay. Let's see what else we have here. So, good. Yes.
What you just wrote, isn't that wrong? Like the last 2 lines?
Yeah. What's the correct thing to write in here? What is the right thing? Right? Correct. Yeah. So this is tricky, right? Yeah. Yeah, that's the easy way to do it for this case. And there's like a lot of, for some cases it might be easier to write this way, in some cases write that way. Depends how many different options there are. So anyway, I'm just trying to warn you by writing this out. It's like you might write down stuff quickly without thinking about it. And it's easy to double count. Like for example, if you put the other term in here, you double count. Because you already have the head. Yeah, you already have the head case here. Right. Right. Yeah, maybe. I'll just write the base theorem down the way you usually see it. So this is the general expression, which is always true. The base theorem way to write it is the probability of A given B is equal to the probability of B given A times the probability of A over the probability of B. and that's just rearranging this equality, just rearranging it. And we'll come back to this, but the situation is, it's like, what's the probability that Professor Green is 5'9", given our measurements, is related to the probability that if Professor Green was 5'9", we would have made the measurements we got. Okay, so this is like the way to invert that statement. All right. And if the thing that's here is exclusive, it means there's like many possible things that could happen. This is probably that one of them happened. If there's a lot of other things that could have happened, for instance, like heads and tails, it's either heads or it's tails. It's exclusive. If it's like that, you could rewrite that probability of B is equal to probability of AI or AJ, probability of B given AJ summed over J. Right? It's just something, whatever A measurement it is, if it ends up with B, that's probability B. Is that all right? So you can put that into the denominator here. You can substitute that in. So you can rewrite this as probability of AI given B is equal to the probability of B given AI times the probability of AI divided by the sum of probability AJ probability of B given AJ. All right. And this is the form that you'll normally see Bayes' theorem in. All right. A lot of times we have a continuous variable instead of discrete events like this. And so then we talk about probability distributions. And so instead of having a sum there, we might have an integral. And this is a topic also is quite confusing to many people. So suppose I have a Maxwell-Boltzmann distribution. I'll have like the probability density of having a certain velocity in the x direction of some particle. Okay? And so that's going to be something like e to the negative 1/2 mvx squared over kt divided by something. All right? Okay? And maybe actually this, I'm not sure, maybe there's a vx here too. You guys remember? I don't know. Something like that. So you have an expression you get for stat mech for probability density. Now what does this mean? We want this thing to be the integral of p of vx dvx over from negative infinity to infinity. We want this to equal something. What do you want this to equal? 1, right? So that means that the units of this is units of centimeters per second. What's the units of this? Centimeters per second and then minus 1, right? It's like, it's per the units of this to get a dimensionless number there. So this has units of seconds per centimeter, which probably none of you thought until I just said that to you. Okay? So probability densities are tricky, and they always have to be multiplied by a delta. You know, when I talk about this, I really need to talk about P of Vx delta Vx. You know, I need to have something here to make this look like a probability again. And so the issue is, it's, you know, the probability that the velocity is exactly something is like 0. It's really the probability that it's in a certain range, plus or minus something. That's then you get a non-zero probability. All right. There's another quantity you'll see a lot called the cumulative probability distribution. So, what letter do we use? Called F. And this would be like the integral from negative infinity to to Vx prime, or Vx, of P of Vx prime dVx prime. And this is the probability that the particle has Vx less than something. So this is F is equal to probability that Vx, let's call this Vx star. Vx is less than or equal to Vx star. And that can be quite an important property. So for example, you're designing a supersonic nozzle. You want to know what gas molecules are going to come out at a certain speed. You really need to know that probability. How many of them are going to be bigger than that speed? How many are going to be less than that speed? Okay. So these are two different ways to express a similar thing. This is like the probability that it does have that speed within a certain range. This is the probability that it has anything less than or equal to that speed. And they're computed different ways. This is an integral. This has units of dimensionless. This has units of per velocity. All right. All right, we'll pick up more on this on Monday.